Which way does it shift?
When it's longer,
It goes higher when?
longer. The longer you put the ball.
The longer. It doesn't have to do with the distance. It has to do with whether it's coming at you or coming away from you. Which way does it shift when it's coming at you? He says higher. We got one vote for higher. Okay. Boom. That's what you get for answering. I don't know if you can or you get that whole. Can try to do it sideways here. Let's see. But you can clearly hear the shift. It's not trivial hearing which way it goes. Let's turn it off. And show you an animation to help with this. It didn't pop up. Let's reset here. So we're going to look at the way I'm going to spin it around. Because like a star is rotating, and so one side is coming at you, the other side comes away. Towards, away, towards, away. And so you ought to hear a Doppler shift, because there's relative motion between you and the edge of the star and this buzzer. When it's coming at you, it should shift which way? What's faster?
Louder.
Not louder, not necessarily faster, but higher frequency, greater frequency. The wave fronts will reach your ear more frequently. The pitch will go up. And then vice versa, or the opposite, when it recedes from you. So we'll hear this pitch. When it's coming at you, you'll hear a slightly higher pitch. When it's going away from you, you should hear a slightly lower pitch.
Are you talking that's the surface of the star, or that's the actual star?
The light from this edge of the star versus this side of the star. Because if this is representing a star that's rotating, the star is going around, right? Yeah, the surface. It can be emitted from below the surface as long as it gets to us. But light emitted from this side is Doppler shifted in a higher frequency, and light from this side is Doppler shifted to a lower frequency. Thus, if you can isolate the light from this side versus this side, you can see that difference. And we're not calculating it, because this is conceptual physics, but how fast or how big that shift is directly related to how fast the motion is between you and the star, or the ball and your ear. The faster you throw the ball, or the faster a police siren's coming at you, the greater the shift. Yeah?
So would lights be brighter if they go towards you?
It's not brighter. Brighter would be amplitude. Amplitude doesn't change. It's still the same volume. It'd be the same brightness. That's amplitude. And, let me emphasize, it's not changing velocity. Light still travels at the speed of light. Sound travels at the speed of sound through its medium. That's not changing. What changed is what we saw change, the frequency and the wavelength. The wavefronts will either get to you closer together and thus be a higher frequency, or vice versa. And I'm glad you asked that, because it's a terminology thing that we get confused on when we say it. Thus, when you guys initially said faster, we relate fast now to velocity, which is why I corrected it. But I knew you knew what you meant. We're referring to frequency. That's the rate. A faster rate would be accurate also. So let's hear it. See if you can hear a shift in frequency. Can you guys hear that all right? And so you can get it with sound, light. It works for all waves. What?
100 mosquitoes.
Yeah, it sounds like mosquitoes. With light, you guys remember, if it's shifted towards you, this side, it increases frequency. Let's say it's visible light. Which side of the rainbow spectrum would it shift to then? Which color has a higher frequency? Do you remember? Yeah, the blue side, the purple end. So let's say you had yellow light emitted. It's a sun, a normal sun, yellow light. Then this side, the light, if it's going fast enough, can actually shift into the green. If it's going even faster, blue or purple, it'll shift that way. Where the light from this side will shift to the orange or the red, which is a longer wavelength, lower frequency. One of my favorite bumper stickers. It's true. It's not on my car at the moment because the paint peeled off and it came with it. But it's a red bumper sticker. You put it on your backside. And it says, if this sticker appears blue, you're driving too fast. Wait for it, Adam. Wait for it. Okay, some of you are getting it. It's not totally funny, but I think it's hilarious. Because the red light emitted from the sticker, if you're driving really fast, you're approaching that vehicle too quickly, right? You're coming together. The frequency should be Doppler shifted up. And the red light would go towards yellow or orange, yellow, green, blue. So if it's going blue, it's getting shifted a lot, which means you're going way too fast. Ironically, you'd have to be going like relativistic speeds, which is impossible, but at this current technology of our world. So yeah, you'd really be going too fast. But it does work, and we've observed it with light, just smaller shifts. Okay. Now, let's do a source, another source. Here's a jet. They go pretty fast. If you just have one, it emits waves. Goes on top of each other.
So the pilot won't hear it?
Correct, the pilot's moving along with it. Let's see, like here, the pilot's up here. So that wavefront never passes him. He's got a lot of other problems to worry about, though, and all the G's pulling on him and everything. But here's an actual picture of a jet right when he exceeds the sound barrier. He doesn't hear it, but what's happened is all those wavefronts have superimposed, and they've compressed the air. Because it's a pressure wave, sound wave. We compressed it. Then they immediately expanded, right? That's what a sound wave does. And when they expand, it cools. When it cools, it gives up some energy. The moisture in the air condenses and it forms a little cloud. So that cloud's from the pressure wave of that shock wave that just passed. Notice the pilot's in front of that. He didn't hear it. But yeah, you're seeing the condensation there from the passing shock wave. Another interesting tidbit some people don't realize is that's what a whip does. It gets thicker and thinner and thinner and thinner. Oh, and then change material even thinner and even thinner. And that allows the wave speed through here to change because we're changing the material that the wave's traveling through. The density of it changes, the flexibility of it changes, and so the wave actually travels faster and faster and faster through the smaller and thinner until right here. And when you do a whip successfully, correctly, this actually breaks the sound barrier, meaning it exceeds the speed of sound. When that wavefront, superimposed wavefront passes your ear, you hear the shock wave. That's a whip. Yeah! That was a good one. So when it makes that sound, that's like a miniature shock wave. The tip is exceeding the speed of sound. All right, let's do some other demos. This one is another way of doing the Doppler effect. It's called a Blugel. It's a toy when you whip it around. But do you hear that wah-wah shift? That's the Doppler effect. These are cool the way they work, and you understand it now. This is moving relative to the air, like an airplane wing through the air, compared to this end. And what happens when air goes across something? Yeah, what principle? Bernoulli's principle. The air is moving faster relative to this, so there's a corresponding decrease in pressure here. Atmospheric pressure here, which is larger, there's now a pressure difference. What's that do to the air? It causes it to flow through the tube. It's like blowing in an instrument. Didn't say it was a good instrument. When it goes through, it hits these corrugations, and that causes the waves to vibrate. Its length determines the size of the wave that gets set up. The wavelength. Remember when we did them on the wave spring? You could see those bumps. Something like that gets set up inside here with the air, and that's the frequency you hear. But it's moving towards you and away from you, so you hear the Doppler effect. Here's some paper bits. If I just hold it in my hand above the bottom here and I spin this top, you can see they get sucked up because of that difference in pressure. There is an airflow through here. The ridges drive the air and cause it to vibrate. If you go faster, let's spin this faster. What should happen? You think the frequency will go up? Why do you think that, Eddie? Good. Yeah, if it's going faster, there should be a bigger drop in pressure, thus a greater difference. Airflow is going faster. Yeah, we're increasing the wave speed in a sense. This is still fixed. So we're having the same standing wave inside. The wavelength's the same. But if you make it go faster, then the frequency will go up. So here's what I did before. If I go faster, There's a lot of good physics in that toy. Let's do this toy. This is one of my all-time favorite toys. All right, Annalee, you want to help? Here, you can stand up where you're at. This is called a space phone. It's awesome. So it'll remind us of the waves. You can do the transverse waves, right? Up and down. You can make the standing waves, because the incident wave and the reflected wave superimpose, they interfere constructively. You can do longitudinal waves by compressing it, and you can see it go back and forth. But this one's great. Go ahead and flick it, Annalee. Yeah, sure. So you can see it and you can hear it. I like doing it with my fingernail. Let's go ahead and talk to it. Hello. Can you hear the echo where you guys are at? Do you think it works with a high frequency? Sure it does.
And with a low frequency. Luke, I am your father.
You want to say something? It's fun.
Did you do that on purpose?
Sort of.
Is that like one of those things?
Thank you. So you get all those echoes. We never actually did the constructive interference live. I showed you the animation. So I'm going to try it here. If I send a wave pulse up like that, you can see it will reflect and come back. Well, I can send one up on this side. They'll both come together. What should happen to the amplitude? And boom! You see how it gets bigger right there in the middle? Boom! Because they're constructively in phase right there. Again. So it gets louder, or more pressure, or brighter if it was a light wave. All right, let's do it the other way. I'll try to do this one up and this one down. That's up here, down. Okay. It's like, patting around or going like this. Opposite direction. I practiced that one. That's harder than it looks. Okay. It looks like they just pass through each other, but for that split second right there, that spot doesn't move. It's destructive interference. Vroom. Vroom. It just stays put. It doesn't get bigger. That's the destructive interference. So when the incident wave and the reflected wave interfere, you can get constructive or destructive interference. If it's constructive, you can get a standing wave. All right, let's do this one. So this is just a stretched out slinky, but it's cool. I can turn the crank and make it rotate around in a circle. Little review here. If I make it go around like this, we'll see what the two-dimensional projection is like. It makes a traveling wave. If I mark a spot, let's see, let's pick this crest right there. I'm going to go around once. See how the handle's up? Let's go around once. Watch that crest. Halfway, whoops, and one. I'm back up. How far did it move? We started here, this was at that point, and now it moved exactly one. So that was one cycle. There's the wavelength. The time that took is the period. Frequency, the inverse of that. If I go faster, if I rotate more quickly, I bet you know what will happen. The wave travels faster. I haven't changed what of those three terms. By me rotating faster, which one of these has not changed? Good. Wavelength. They're still spaced the same. That doesn't change whether I spin it fast or slow. But if I go faster, what increases? Yeah, the velocity, it's clearly moving faster. You can see that. But it also gets to the paper clip more quickly. Boom, 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 boom. So the frequency goes up too. Again, just to show you how this can guide our thinking. It's a fixed wavelength. You change one of these, the other one has to change. All right. Well, Doppler effect was the last thing in chapter 19. We're already like mostly through 20 because it's the same concepts. Let's do this. 15 minutes? Okay. You've heard this. If a tree fell in the woods and no one was around, would it make a sound? You guys say yes? But if you're not there to hear it, is there a sound? It creates sound waves. That much has to be true, right? So I'm with you guys. Yeah, of course it makes a sound. The only time people argue with this is their definition of sound. Is it subjective? In other words, there's no sound unless I hear it, unless it makes my eardrum vibrate, which then hits my ossicles, the hammer and the anvil and the stirrup. And then they hit the basilar membrane, which causes the fluid inside to a wave go through that. And then as that wave travels across, they hit the hair cells in there, and it makes them move. And then they send a signal, an electrical signal to your brain. Boom, I heard something. Is that the only time there's a sound? That's when the only time people have an argument with this, is their definition of sound. And for us in physics, a sound wave is a longitudinal wave with compressions and rarefactions. That's all there is to it. Whether there's someone there to actually hear it or not, there's still an actual sound wave produced. So yeah, I would say it makes a sound. And so would all other scientists anyway.
So with light waves, there's like a visible spectrum that you can see. Is there some sort of similar thing with sound waves where there's different types of frequencies that you can
I'm glad you asked. That's this demo. We'll do it. Turn that on. Takes a minute to warm up. This is an old frequency generator that uses vacuum tubes. It's great. The reason I use it is because they don't make them like this anymore, where you can do a bigger range of frequencies without having to stop and reset and go up higher. This will do it all in one turn. So you asked, with light, there's lots of frequencies of light, but we can only see this many in the visible range. How about with sound? Yeah, we can only hear sound between 20 and 20,000 hertz. A healthy, normal person. And usually when we're younger. As we get older, that narrows because of damage to our ears. But we hear 20 to 20,000 hertz. So if it's below 20 hertz, we can't hear it. We say it's ultrasonic. Infra. I knew I was using the wrong word. Infrasonic. Infra is below. Ultrasonic is above. Anything above 20,000 hertz is ultrasonic. We don't hear it. These would have shorter waves because they're higher frequency. These would have longer waves because they're lower frequency. And so this, we can demonstrate that. I got an amplifier and a speaker. Okay, this is 200 hertz. 200. Can you guys hear it? All right, let's go down to 20. Okay, raise your hand if you can hear that. I can't. Of course, I'm behind it too, but... So we're going to play a game. Raise your hand when you can hear it. Put your hand down when you can't. And you can find out your range. I mean, it's not a perfect speaker, but we'll get the idea. So I'm going to not change the amp. Well, hold on. Okay. I'm not going to change the amplitude or the volume. I wanted to get it set for the other frequencies. All right, anybody hear that? Okay, you're consistent at least. He says he still hears it. We're at 30 hertz. 50. Come on, get them high. Come on. 100. 2. 500. 1,000. 2,000. 3. 5. 10,000. We lost a couple. Still increasing. We're losing folks now. We're around 16,000 hertz. My daughter can still hear these because she says it's annoying. Still increasing, not to 20 yet. Anybody still playing? You can still hear it? Okay, we'll be quiet. Can anybody still hear it? Oh, good. You're the first ones that never lied. So I got to 20,000 hertz and then I stopped. And then what I usually do is there's always a couple with their hands still up. So then I turn the volume off. They go, yeah, I can still hear it. It's not doing anything. But that's good. So yeah, that's usually where our damage happens. This usually lowers as we get older, the high frequencies. And once you damage those hair cells, if you have too loud of music for too long, those hair cells that vibrate inside there break. They don't regrow back. And so once you've lost it, you've had hearing damage, it's gone. And so that can happen with prolonged exposure to loud sounds. All right. So there's that range of frequencies. That's what sound is. Pitch is subjective. Compressions, rarefactions, you know all that. All right, let's talk about the speed of sound through things. Sound waves are the vibrations. The source of all waves is a vibration. Something has to be vibrating. I'm going to use these dominoes as an example. We've mostly been talking about the sound through air. But sound travels through solids and liquids. You can hear things underwater. Any of you put your ear to the railroad track? You ever done that? Nobody in here's ever done that? To hear the train coming? Yeah, it's because you get a fine if you do it with tracks. But well, I used to. And you can hear the train coming. It's really true. Way further away that way than you can listening through the air. One reason is energy is dissipated more in the air. It doesn't travel as far. It also doesn't travel as fast through the air. But if you listen to the metal, the rail, hasn't lost as much energy due to the friction in the material, and it travels faster. So you can tell it's coming from a long ways away before you can tell this way. An object's internal energy, that internal energy, part of that would be the vibrations. Well, we said that. Yeah, and it's those vibrations. It's that medium. They're made up of molecules, particles, atoms. And the only way sound can transmit is by, boom, running into this one, right? Making it wiggle. It hits its neighbor, makes it wiggle. Boom, boom, boom. And it's those interactions that transmit the wave. Remember, individually, they're just doing this, right? The rods are just going up and down. But they're connected to their neighbors, and so they influence their neighbor. The wave, though, is what travels. Energy can travel with a wave, not the matter. So they're just kind of wiggling, hit their neighbor. Hey, stop it. Stop it. And it travels. So the speed in a material depends on the density of the material. So that's where my dominoes come in. Thought of this one a couple years ago. So these are like really dense. You see how there's a lot of matter in a smaller space. So it's more dense. Where they're spread out. This would be like two different materials. If I hit them at the same time, who do you think will get to the end first? Which one will the wave travel faster through? 2 votes for denser. Nobody else voting, huh? All right, this happens quickly. And it's not sometimes not a huge effect. So watch. See who gets to the end here. Are you ready? 1, 2, 3. Who won? More dense. You were right. And that was a good one. That was more clear. So that's how I remember how sound travels. It's the interactions. These, it doesn't have to move as far before it interacts with its neighbor. So the wave can be transmitted more efficiently, or quickly, I should say, through it. That's why it got through this one faster. Where the ones that were farther apart, physically, this had to fall further before it hit it. Takes longer. They're not as close. There's less interactions. And so it took longer to get through it. That's how you can remember the speed of sound. So let's think of some things. Air and metal, or air and solids for that matter. Solids, more dense. So sound travels faster in solids generally than air. It would travel quicker in liquids than air too, right? Because they're closer together. What if you change the temperature? Let's take air. If you heat air up, will sound travel faster or slower? Slower. Why? It expands. Yeah. Yeah, if you contained it, and if it couldn't expand, then it wouldn't change its density. Yeah. Yeah. So I was allowing it to be free, yeah. Or you take a metal rod, heat it up, it'll expand. It becomes more like this, and yeah. So temperature can affect that density and thus the speed of sound. That's why when we say the speed of sound in air, you should give the temperature of the air, because it depends on the temperature. Your author gives yeah, let's do... Nah, I'll do that Monday. So any elastic substance can transmit sound. Any elastic. I want to specify, that means it can spring back. It doesn't necessarily mean it's stretchy. Some people get that confused. Stretchiness is not the same as elastic. Because you can stretch something, and if it doesn't spring back, it's not elastic. It has to be able to do that vibration to transmit the sound through. So if you just stretch something and it stays there, or just kind of, it can't bounce back to affect its neighbors. So here's a cool one you can do. We got this relationship. What is the speed of sound? Well, the speed of sound is, let's move this. .330 meters per second at 0 degrees Celsius. Let's look at room temperature, because that's what we usually deal with. Room temperature is around 20 degrees. And this is in your book if you forget. Should this go up or down? It's hotter now. Will it go faster or slower? You guys just answered this when I said we took warm air and it expanded. Boy, I need a weekend too. Yeah, well. Okay, I got some explaining to do. It goes faster. Yeah, see, it still gets me today. Okay. That's what I overlooked. Okay, I got it. So I apologize for confusing you, and let me explain it. So you heat it up, it will expand. That's true. So that in and of itself, everything we said was right. What I forgot though, when you heat something up, what do those particles start doing? They start moving faster. They have a greater temperature, so a greater average translational kinetic energy. That's going to dominate, and that's what I overlooked. So again, let's look at the interactions to be consistent. Here they were so close together, moving at certain speeds, and so it went through it at a certain rate. Now they might be a little farther apart, but they're moving with a lot more energy. Velocity squared, the kinetic energy is that squared term. And so if you bump one of them, it's going to cause it to wiggle, but it's already moving faster. So it's going to wiggle faster and hit its neighbor more quickly than it would if it was colder. That's how we can think of this and how I should have explained it. Does that make sense? Since they're all moving faster, the interactions will occur more quickly, thus allowing the wave to travel through it faster. So with hot air that can expand, they're moving faster. And I totally blew it. Hot things have more energy, they will go faster through it because of those interactions. So 340 meters per second. Well, the reason I wanted to share that was because the last thing I have time to do, when you hear thunder and lightning, you can gauge how far away the thunder was, or the lightning was. Thunder makes a sound wave that takes the air to travel through at a different speed, this speed roughly, depending on the temperature, versus light, which is super fast. That's why you can see the lightning before you hear it. So use that. How many seconds does it take from when you see the lightning before you hear the thunder? Well, velocity is distance divided by time, right? If you know the speed that the wave's traveling at, right? And you time how long it took to get to you, because essentially, for this purpose, the light was almost instantaneous. So as soon as it flashes, you see it almost right away. So from then to by the time that wave gets to you, you just time it like 1001, 1002, 1003. So the distance, u r away, is that velocity times time, 340 meters per second for 3 seconds. What do you get? I did that one. Which is roughly a kilometer. So that's what I use. For every 3 seconds you hear, the lightning was about a kilometer away. If you're going 1001, 1002, 1003, 1004, 1005, 1006, then you hear it. You know, because of the wave speed, it was 2 kilometers away. And you should take cover because you're too close. So it still works the same way. It's still a wave velocity. And these speeds will tell us how long it takes to get through stuff. And how fast that speed is depends on the interactions in the material. The more interactions there are, the more quickly it tends to get through. All right, have a great weekend.